In the previous slide, the target space was a line V. In this slide, we are interested to project B on the space or on the column space of A. Specifically, we are interested to solve Ax equals to B. When the vector B is not in the column space of A, there is no solution. Instead, we find the least squares solution, and we know from past slides and past lectures that the least squares solution can be found by the normal equation. When this is found by the normal equation, the error is orthogonal to the surface, the column space of A. In other words, we are projecting B onto the column space of A, and the error is orthogonal to the surface of A, and this situation is exactly the same as the previous slide, where the space we're interested in was only a line. Now, through the normal equation, we found that the best x hat satisfy this normal equation if A transpose A is invertible, that is, A transpose A inverse exists, then we can multiply both left hand side and right hand side on the left by this inverse matrix, allowing us to get x hat equals to this equation here. A transpose A inverse A transpose B is x hat. Now, once we have gotten x hat, we can substitute x hat as x, basically allowing us to do this: A multiplying by this whole matrix, A transpose A inverse A transpose B, to get B hat, where B hat is this matrix A multiplied by x hat, and x hat was how we have found it using this equation. Now at this point, compare this equation with this equation here. We're now in a position to identify the projection matrix. Let me circle it for you. This is the projection matrix. B hat is equals to the projection matrix multiplied by B. That's the interpretation. B hat equals to A x hat is equals to the projection matrix multiplied by B. Using the projection matrix idea, the input is B. Multiplying projection matrix PB will get B hat. So we now have identified the projection matrix, given that the input space is spanned by columns of A, derived using the least squares solution. In the next slide, we talk about some properties of the projection matrix. It has two interesting properties. A projection matrix is a square matrix first, and not only is it a square matrix, its transpose is equals to itself. P transpose is equals to P. Not only that, P multiplied by P is equals to P. P multiplied by P multiplied by P n times is still equals to P. So it is called the idempotent property of the projection matrix. These two properties together are the properties that will always exist when we say that a matrix is a projection matrix. You can have a look at lecture 16 of Strengths 1606 Linear Algebra 2010 video series, where he talked about projection matrices and the least squares.